Right now, as you watch this video, 20,000 galaxies are disappearing every second. Not dying, not fading, but slipping past an invisible boundary where no light, no signal, and no information can ever return. By the time I finish this sentence, another 100,000 galaxies have joined the unreachable vastness. The universe is 99% empty, and it is becoming even emptier. This is not the far future. This is happening right now. The void is not quiet emptiness. It is an active force swallowing everything we know, and there is nothing anyone can do to stop it. The void, a deep journey into the emptiness that is consuming everything. But before we begin, do not forget to subscribe. And if you truly enjoy these videos, please leave a like. Let us begin. What you are about to learn will change the way you look at the night sky forever. You think you are looking at a universe full of stars and galaxies and light. You are wrong. You are looking at almost nothing. The universe is 99% empty and becoming emptier with every passing second. Not slowly, not bit by bit. Galaxies are slipping beyond an invisible boundary right now as you listen to these words. And they will never come back. The void is not passive. It is not just the lack of matter. It is an active force consuming everything we know and everything we will ever know. By the end of this investigation, you will understand why isolation is not something waiting in the far future. It is already here. It is already happening, and there is nothing anyone can do to stop it. Let us begin with the greatest emptiness ever discovered. Chapter 1. The Great Nothing. Imagine you could travel at the speed of light, 300,000 km/s, fast enough to circle Earth more than 7 times in a single heartbeat. You aim your spacecraft toward a region of space in the direction of the constellation Bootes. The herdsman, that ancient pattern of stars visible in the northern sky. You speed up. You pass the outer planets. You leave the solar system. You move into interstellar space where the nearest star is more than 4 light years away. You keep going decade after decade, century after century, and then something strange begins to happen. The stars start to thin out, first slowly, then suddenly. The familiar glow of the Milky Way fades behind you. The scattered points of light that should surround you in every direction begin to vanish. You travel for millions of years at the speed of light, and you see almost nothing. No galaxies, no clusters, no filaments of cosmic structure, just darkness. Endless, even, crushing darkness stretching in every direction for hundreds of millions of light years. You have entered the Bootes void, the Great Nothing, the largest known empty structure in the observable universe. A spherical region of space about 330 million light-years wide. To understand that size, think about this. The Milky Way galaxy is about 100,000 light-years across. You could fit the entire Milky Way inside the Bootes void more than 3,000 times and still have space left over. You could fit our entire local group of galaxies, including Andromeda and all its companions, and it would be a tiny dot lost in the darkness. This void makes up about 0.35% of the entire diameter of the observable universe. That sounds small until you realize the observable universe is 93 billion light-years across. In 1981, astronomer Robert Kirshner and his colleagues at the University of Michigan were carrying out a redshift survey. They were mapping the positions of galaxies in 3 dimensions, measuring how fast they were moving away from us, calculating their distances, and building a picture of the large-scale structure of the universe. And then they found a hole, a region where the galaxies simply stopped. At first, they thought it was a mistake. Maybe their instruments were not working correctly. Maybe a cloud of dust was blocking their view. They checked and checked their data again. They looked once more. The hole was real. What they discovered changed our understanding of the universe forever. The Bootes void should contain about 2,000 galaxies based on the average amount of matter in the universe. It contains about 60. Just 60 galaxies in a space where there should be 2,000. And even those 60 are not spread randomly. They cluster together in a strange, tube-like shape running through the center of the void, as if they are leftovers of walls that once separated smaller empty bubbles before those bubbles merged into one huge nothing. Think about what this means. If the Milky Way had formed at the center of the Bootes void instead of where it really is, human civilization would have grown under very different stars. Or more accurately, under almost no stars at all. Astronomer Greg Aldering calculated that if we lived in the heart of this void, we would not have known other galaxies existed until the 1960s. For all of human history, we would have looked up at the night sky and seen only the stars of our own galaxy surrounded by complete blackness. No Andromeda blur visible to the naked eye. No distant spirals revealed by early telescopes. Just our lonely island of light floating in an ocean of nothing. The universe would have looked completely different, smaller, more isolated, more alone. But here is the key point. The Boot's void is not unusual. It is not a strange accident. It is simply the largest example of something that controls the structure of the entire universe. When astronomers map the universe on the largest scales, they do not find matter spread evenly like sugar mixed into water. They find a cosmic web. Galaxies gather together in long strands and dense knots called superclusters. These structures twist and connect across billions of light years like the threads of a massive spider web. And between those threads, filling the spaces between the filaments, are voids. Hundreds of thousands of voids, maybe millions. The voids make up about 80% of the volume of the observable universe. Read that again. 80%. When you look at the night sky and admire the stars, you are looking at the rare exception. You are looking at the 20% where matter managed to gather together. The other 80% is emptiness. Cosmic deserts stretching for hundreds of millions of light years in every direction. Cold, dark, and nearly empty of anything we would call matter. The universe is not a sea of galaxies with a few empty gaps. It is a sea of nothing with a few islands, and those islands are drifting apart. The voids are not frozen in place. They are growing. Every void in the universe is expanding, pushing the strands of matter farther apart, stretching the cosmic web thinner and thinner. New voids form as smaller empty bubbles join together. Existing voids expand outward as the space inside them grows faster than the space inside denser regions. The universe is not just empty, it is becoming emptier. Why does this happen? The answer begins at the very start, 13.8 billion years ago. In the first tiny moment after the Big Bang, the universe was almost perfectly even. A hot, dense mix of energy and matter filled all of space with nearly the same density everywhere, but not exactly the same. Quantum fluctuations, the built-in randomness of reality at the smallest scales, created tiny differences. Some regions were slightly denser than average, others were slightly less dense. These differences were extremely small, maybe 1 part in 100,000, but they mattered. Gravity makes differences grow. A region that is a little denser has a little more mass and therefore a little stronger pull. It attracts matter from nearby regions and becomes denser still. The regions it pulls matter from become even less dense. They have weaker gravity. They lose more matter. Over billions of years, this process repeats again and again. The dense regions become denser. The thin regions become thinner. Tiny differences become huge ones. Fluctuations turn into filaments and voids. The cosmic web we see today is the frozen imprint of quantum randomness from the first moments of existence. The voids are not empty because matter was taken away from them. They are empty because matter never gathered there in the first place. They represent the losing side of a cosmic lottery that played out over billions of years, and they are winning now. The expansion of the universe favors emptiness. It stretches space faster in regions where there is less matter to resist the stretching. The voids grow, the filaments thin. The islands of matter become more isolated. Think about what scientists found when they searched for even larger voids. In 2015, a team of astronomers looking for an explanation for a strange cold spot in the cosmic microwave background radiation found evidence of a structure that is even bigger than the Boot's void. The Eridanus supervoid, located in the direction of the constellation Eridanus, appears to be about 1.8 billion light-years across. 1.8 billion. That single void spans almost 2% of the diameter of the entire observable universe. If confirmed, it would be the largest known structure of any kind in the universe. Not the largest cluster of galaxies, not the largest filament of matter, but the largest empty space. The largest nothing. We live in the local group of galaxies, a small collection of about 80 gravitationally bound systems led by the Milky Way and Andromeda. Our local group sits on the edge of its own void. The local void, a region of relative emptiness that stretches for about 60 megaparsecs. We are not at the center of cosmic civilization. We are on the edge of a cosmic desert. And that desert is pushing us. Measurements show that the Milky Way is moving away from the local void at about 260 km/s, pulled toward denser regions and pushed away from emptiness. The void shapes our movement through space. It shapes the evolution of our galaxy. It shapes the future of everything we will ever observe. But the voids we see today are only the beginning. What makes cosmic emptiness truly frightening is not how big it is now, but what it is becoming. Something is speeding up the expansion of the universe. Something is pushing the voids to grow faster and faster. Something is making sure that emptiness will one day take over everything. That something has a name, dark energy, and it is the most abundant thing that exists. In the next chapter, we will explore the structure of emptiness itself, how the cosmic web formed, why matter clusters the way it does, and how we discovered that the universe is not just expanding, but speeding up toward a future where nothing remains except the void. The story is only starting. Chapter 2. The Architecture of Emptiness. Stand at the edge of a beach and look at the foam left behind by retreating waves. Notice how the bubbles gather together, how their walls touch and merge, how the spaces between them form a delicate network of films and empty gaps. Now stretch that image to the largest scale you can imagine. Billions of light years, trillions upon trillions of galaxies. The cosmic web that links everything looks surprisingly similar. Bubbles of emptiness surrounded by thin walls and strands of matter. The universe is foam, and like all foam, it is mostly air. The discovery of this structure came slowly, built from decades of careful observation. In the 1970s and 80s, astronomers began carrying out large surveys of galaxy positions. They were not just listing individual objects, they were mapping the landscape of the universe. What they found shocked everyone. Galaxies were not spread randomly like dust tossed into the air. They were organized, grouped, connected. The first major surveys revealed superclusters, huge collections of hundreds or thousands of galaxies stretching across hundreds of millions of light years. The Virgo supercluster, which includes our own local group, stretches about 110 million light years across and contains roughly 100 galaxy groups and clusters. The Shapley supercluster, the densest known concentration of matter in the nearby universe, lies about 650 million light years away and contains more mass than any other similar region we have mapped. These structures are not alone. They link to one another through filaments, long chains of galaxies that stretch across space like bridges between islands. And between them lies nothing. The voids were first thought to be rare mistakes, places where matter simply failed to gather by chance. But as surveys became larger and more complete, astronomers realized the truth. The voids are not the exception, they are the rule. The cosmic web is not a thick forest with a few clearings. It is a thin network of threads surrounding enormous bubbles of emptiness. Picture the largest computer simulations of cosmic structure. The Millennium simulation run in 2005 modeled more than 10 billion particles representing dark matter across a region of space, about 2 billion light years on each side. The results created images that have become famous in cosmology. Glowing strands of matter surrounding dark, round voids. A universe that looks like neurons in a brain, blood vessels in tissue, or foam in a cup of coffee. The physics that creates this pattern is simple and harsh. In the beginning, matter and dark matter were spread almost evenly through space. But the tiny quantum fluctuations from the first moments after the Big Bang planted seeds, regions that were slightly denser. Gravity grabbed those seeds. Matter fell inward. Dark matter, which does not interact with light and passes through normal matter like a ghost, collapsed first. It formed halos, huge invisible structures that became the framework for the visible universe. Ordinary matter followed, falling into the gravity wells shaped by dark matter. The first stars lit up. The first galaxies formed. But here is the key idea. Gravity is not fair. It does not pull everything equally. It creates winners and losers. A region with slightly more matter pulls harder than its neighbors. It steals matter from them and grows stronger. The neighbors grow weaker. The strong grow stronger. The weak grow weaker. This runaway gravity shapes the universe at every scale. Think about a flat field after rain. Water flows downhill, gathering in low places. Low places become streams. Streams join into rivers. Rivers carve deeper paths that pull in even more water. The land develops structure, ridges between valleys, networks of channels linking pools. The cosmic web forms through a similar process, except instead of water flowing downhill, matter flows toward gravity wells. Instead of streams, there are filaments. Instead of pools, there are galaxy clusters. Instead of ridges, there are the walls of voids. The filaments are rivers of galaxies. They guide matter from voids toward the densest points of the cosmic web. Gas moves along them, feeding the growth of new galaxies where they meet. When filaments meet, they form clusters, the big cities of the cosmic web, where thousands of galaxies pack together in regions only a few million light years wide. The Coma cluster, one of the nearest large clusters to us, contains more than 1,000 known galaxies squeezed into a region about 20 million light-years across. Compare that to the Boot's void. Almost the same number of galaxies spread across a space more than 3,000 times larger. The difference between fullness and emptiness could not be clearer. And yet, even the densest clusters are mostly empty. This is the second layer of cosmic emptiness, the one hidden inside the structures themselves. A galaxy cluster sounds crowded, thousands of galaxies in a small space, but remember the scale. Galaxies in a cluster are separated by millions of light-years. The space between them is vacuum. Even inside a single galaxy, emptiness rules. The Milky Way holds about 200 billion stars. It seems incredibly full when you look at the glowing band across a dark night sky. Yet, if you traveled from our sun to the nearest star, Alpha Centauri, at the speed of light, the trip would take more than 4 years. At the speed of the fastest spacecraft humans have built, it would take tens of thousands of years. Stars are tiny points separated by huge oceans of nothing. Go smaller still. Inside every atom, the nucleus takes up about 1/10,000th of the atom's width. The electrons that move around that nucleus are not solid objects, but fuzzy clouds of probability spread across the rest of the space. If you could enlarge an atom to the size of a football stadium, the nucleus would be a marble sitting at the center of the field. Everything else would be empty. The chair you sit on, the screen you watch, the body reading these words right now is almost entirely empty space, held together by electric forces that create the feeling of solidity. The universe is empty at every scale, void within void within void. But the voids on cosmic scales are special because they are growing. Imagine stopping time and taking a picture of the universe today. Mark the position of every galaxy, measure every distance. Now move time forward by 1 billion years and take another picture. Compare the two. What has changed? The clusters will have evolved, some galaxies will have merged. Stars will have been born and died. But the biggest change will be in the distances. The empty spaces will be larger. The filaments will be more stretched. Galaxies that were once close neighbors will have drifted apart. This is cosmic expansion. Space itself is stretching, carrying everything with it. Edwin Hubble discovered this in 1929 when he saw that distant galaxies were moving away from us. And the farther away they were, the faster they moved away. The relationship was simple. A galaxy twice as far moved away twice as fast. This became Hubble's law, the foundation of modern cosmology. It told us the universe has a history. It was once smaller, denser, and hotter. Trace the expansion backward in time and you reach a beginning, a singularity, the Big Bang. For decades after Hubble's discovery, astronomers assumed the expansion was slowing down. After all, gravity pulls everything together. The matter in the universe should be slowing the expansion like friction, slowing a spinning wheel. If there was enough matter, the expansion might eventually stop and reverse, leading to a big crunch where everything collapsed back into a singularity. If there was not enough matter, the expansion would continue forever, but always slow down, getting closer to zero speed in the infinite future. Either way, the rate of expansion should be decreasing. In 1998, 2 teams of astronomers independently proved that assumption completely wrong. They were studying type supernovae, the explosions of white dwarf stars that reach a predictable peak brightness. Because their true brightness is known, the supernovae can be used as standard candles. Measure how bright they appear compared to how bright they really are, and you can calculate their distance. Compare that distance to their redshift, the stretching of their light caused by cosmic expansion, and you can measure how fast the universe was expanding at different times in its history. The teams expected to find that expansion was slowing. They found the opposite. Distant supernovae were dimmer than expected, not brighter, dimmer. This meant they were farther away than they should be if the universe had been slowing down. Something was pushing them away faster than gravity could pull them back. Something was speeding up the expansion of the universe. This discovery won the 2011 Nobel Prize in Physics. It also frightened cosmologists because it meant the universe contained something they did not understand. Something that fought against gravity, something that was causing the empty spaces to grow faster and faster with each passing moment. They called it dark energy, and it makes up about 68% of everything that exists. Think about that number, 68%. More than 2/3 of the entire universe is made of this mysterious force that pushes space apart. Only about 5% is normal matter, the atoms that make up stars and planets and people. The remaining 27% is dark matter, the invisible framework that shaped the cosmic web. We are the cosmic minority, a thin layer of complexity floating on an ocean of dark substances we cannot see, touch, or explain. Dark energy changes everything about the future of the empty spaces. Without dark energy, the cosmic web would change slowly. Voids would grow, but their expansion would slowly slow down as the gravitational pull of distant matter applied its gentle braking force. Given endless time, the universe might reach a kind of balance. A huge web of matter stretched thin but still connected. With dark energy, that future is impossible. The acceleration is exponential. Space is not just expanding, it is expanding faster every year. The voids are not just growing, they are growing faster every year. And because dark energy seems to be a property of space itself, the more space exists, the more dark energy exists. Expansion creates more space. More space creates more dark energy. More dark energy creates faster expansion. It is a feedback loop with no end. In the current era, about 7 billion years after dark energy began controlling the expansion, galaxies are separating from each other at an ever-increasing rate. Superclusters that were once held together by gravity are being pulled apart. The filaments of the cosmic web are stretching thinner. The walls of the voids are breaking apart. And at a certain distance, something even more disturbing is happening. Galaxies are disappearing. Not dying, not fading, disappearing, crossing an invisible boundary from which no light, no signal, no information can ever return. We call this boundary the cosmic event horizon, and it is swallowing the universe, one galaxy at a time, right now. In the next chapter, we will study this horizon. We will learn why the observable universe is shrinking even as space expands. We will understand why we are already cut off from 94% of the cosmos and why that isolation will only grow. The void is not waiting in the future. It is consuming the present. Chapter 3, the force that pulls apart. There is a number that troubles cosmology. About 160 billion. That is how many stars cross the cosmic event horizon every single year. 160 billion stars spread across countless galaxies, passing beyond the boundary of anything we can ever hope to reach. They are not destroyed. They continue to exist. Their planets still orbit. Their civilizations, if any, still exist, still rise and fall, but they are lost to us forever, and we are lost to them. The speeding up expansion of the universe is not a slow drift. It is an active cutting, a breaking of connections that can never be repaired. To understand what is happening, we need to study the strange physics of an expanding universe and the even stranger force that is speeding up that expansion. Start with a simple thought experiment. Imagine the universe as an endless rubber sheet with coins glued to it. Each coin represents a galaxy. Now stretch the sheet evenly in all directions. What happens to the coins? They move apart. Not because any single coin is moving across the sheet, but because the sheet itself is stretching. Every coin sees every other coin moving away from it. The farther away a coin is, the more sheet lies between them, the more that middle sheet stretches, and the faster that distant coin seems to move away. This is how cosmic expansion works. Galaxies are not flying through space like bullets shot from a gun. Space itself is stretching, carrying the galaxies with it. The galaxies stay still within their local space. But that local space is being carried away from other local spaces by the expansion of the space between them. Now here is where things get strange. Stretch the sheet fast enough and something surprising happens. Distant coins can seem to move away faster than any speed limit. In our universe, no object can move through space faster than light. But space itself has no speed limit. It can stretch as fast as physics allows. And physics allows it to stretch extremely fast. Calculate the speed at which a galaxy at the edge of the observable universe is moving away, about 46 billion light-years away. Include the expansion rate, both past and present. The number you get is greater than the speed of light, much greater. Those distant galaxies are moving away from us at speeds greater than 300,000 kilometers per second. They are not breaking relativity. They are not moving through space faster than light. Space is carrying them away faster than light can travel through that space. This creates a horizon. Imagine you are standing on the surface of the rubber sheet. You want to send a message to a distant coin. You send the message at the fastest possible speed, the speed of light. The message races across the sheet toward its target, but the sheet is stretching. New sheet is forming between the message and its destination faster than the message can cross it. The message never arrives. It travels forever through expanding space, always falling behind, eventually being carried backward compared to its target as the stretching overpowers its motion. The cosmic event horizon is the distance where this happens. Beyond this boundary, any signal sent today will never reach a distant galaxy, and any signal sent from that galaxy will never reach us. The galaxies are not hidden behind a wall. They are not blocked by dust or hidden by matter. They are simply unreachable. The expansion of space has made contact impossible. The current distance to the cosmic event horizon is about 16 billion light-years. This is much smaller than the size of the observable universe, which reaches about 46 billion light-years in every direction. We can still see light from galaxies beyond the event horizon because that light was sent long ago when those galaxies were closer and the expansion was slower. That ancient light has been traveling toward us for billions of years, and we receive it now as pictures of the distant past. But any light those same galaxies send today will never reach us. We are seeing their history, not their present, and we will never see their future. Here is the troubling meaning of this. Of all the galaxies we can currently observe, about 94% are already beyond the cosmic event horizon. They are already unreachable. The light we see from them is a fossil, a record of a past moment frozen in time. The galaxies themselves have moved on, grown, changed in ways we will never see. If intelligent civilizations exist in those distant galaxies, if they are looking back at us, they see a similar fossil. They see the Milky Way as it was billions of years ago. They will never know what we have become, and the horizon is moving closer. Because the expansion is speeding up, the event horizon is not fixed. It is shrinking. Galaxies that are currently reachable are crossing the line into permanent isolation. Every year, the amount of space we can ever hope to interact with gets smaller. Every year, more of the universe slips beyond the cosmic curtain. Run the numbers forward. In about 150 billion years, every galaxy outside our local group held together by gravity will have crossed the event horizon. The Virgo supercluster, the huge structure that contains our local group, will be torn apart. The filaments of the cosmic web that now connect us to distant clusters will stretch beyond what we can see. Future astronomers, if any exist, will look out at a sky that contains only the merged remains of the local group and nothing else. No distant galaxies, no cosmic microwave background that can be detected with any technology, no proof that the universe ever held anything beyond their lonely island. The great irony is that this future civilization would develop cosmology under completely different conditions. They would see a motionless universe, a single giant galaxy floating in an endless void. They would have no redshift data from distant galaxies because there would be no visible distant galaxies. They would have no cosmic microwave background because its wavelength would be stretched beyond detection. They would have no way to figure out the Big Bang or measure the expansion of space. The evidence we depend on, the data that lets us rebuild the history of the universe, will have been erased by the same expansion that created it. We live in a special time, a short window of cosmic history when the universe shows its secrets to careful observers. We can see the cosmic microwave background, the afterglow of the Big Bang, stretched but still detectable. We can see distant galaxies, redshifted but still visible. We can measure the expansion rate, calculate the age of the universe, rebuild the history of structure formation. Future civilizations will have none of this. They will inherit a universe that appears motionless, eternal, and alone. But what is causing this speeding up? What is dark energy? The honest answer is that we do not know. The simplest idea comes from quantum field theory. Even empty space, a true vacuum, is not really empty. Tiny particles appear and disappear constantly, borrowing energy from reality for the briefest moments. This quantum activity gives empty space a basic energy, a kind of cosmic background noise that fills all of space. Einstein's equations of general relativity allow for a term called the cosmological constant, a fixed energy of empty space that would cause expansion to speed up exactly as we observe. The problem is that when scientists calculate the expected value of this vacuum energy using basic theory, they get an answer that is wrong by about 120 orders of magnitude. Not twice as big, not a million times off, but 10 raised to the power of 120. This is likely the worst prediction ever made in science. Something is very wrong with our understanding of quantum mechanics, general relativity, or both. Other explanations exist. Perhaps dark energy is not constant, but a changing field that evolves over time. Scientists call this field quintessence, a fifth essence beyond the four classic elements. Perhaps gravity behaves differently on the largest scales than our theories predict. Perhaps we live in a universe with extra dimensions we cannot see, and dark energy leaks in from physics we cannot reach. Perhaps the universe is not uniform on the largest scales, and what we see as acceleration is really an effect of where we are located. None of these ideas has been proven. None has been ruled out. We are left with a universe where the most common ingredient is also the most mysterious. What we do know is the result. Space is expanding. The expansion is speeding up, voids are growing, galaxies are separating, and the rate of separation is increasing. Think about what happens to a particle of light moving through this speeding up expansion. Light has a wavelength, the distance between the peaks of its wave. As space stretches, the wavelength stretches too. Red light becomes infrared. Infrared becomes microwave. Microwave becomes radio. The light loses energy as it redshifts, its frequency drops, and its effective temperature cools. Now think about a photon sent from a galaxy just inside the cosmic event horizon. That photon moves toward us while space expands both behind it and ahead of it. It struggles through stretching space like a swimmer in a river whose current grows stronger every moment. If the photon reaches us at all, it arrives with its wavelength greatly stretched. A photon that started as blue visible light may arrive as infrared or radio. Its energy has been drained by expansion. As galaxies near the event horizon, their light redshifts without limit. They seem to freeze in time, their light stretched to longer wavelengths, their images becoming dimmer, their clocks seeming to slow as relativity takes effect. They do not suddenly disappear, they fade. They redshift into invisibility. They become ghosts, then memories, then nothing. And there is nothing we can do to stop it. No technology we can imagine can beat the expansion of space. Traveling at the speed of light would not be enough. The event horizon is defined by where light itself cannot reach. Even if we could send signals at the speed of light, we could not talk to galaxies beyond that boundary. Even if we could somehow move faster than light, we would break the basic laws of physics as we understand them. The cosmic event horizon is not like the edge of a black hole, which is set by light being unable to escape a small region. The cosmic event horizon is everywhere. It affects everyone. It guarantees that as the universe grows older, isolated groups of matter will drift alone through an emptier universe, cut off from everything else that exists. This is the force that pulls apart. Not a force in the usual sense, not a push or a pull on objects, but an expansion of the stage itself. A stretching of the space in which all forces act. Gravity pulls matter together, but expansion pulls regions of space apart faster than gravity can pull them back. And expansion will win. In the contest between gravity and dark energy has already taken the lead. The universe changed from matter-controlled expansion to dark energy-controlled expansion about 5 billion years ago. Since then, the acceleration has been steady and unstoppable. The voids grow larger. The filaments stretch thinner. The distances between unbound galaxies grow by about 0.007% every million years. It sounds tiny. Over billions of years, it is devastating. The isolation we face is not a far future idea. It is a real process happening now. Every second, galaxies that might have been reachable become unreachable forever. Every minute, the space we can ever interact with shrinks. Every year, 160 billion stars, their planets, and their possibilities vanish beyond the curtain. The void is not empty silence. It is an active force that eats away at the connections that make a universe a universe. In the next chapter, we will look at what this means for our horizon. We will learn why the observable universe is not the entire universe, why we can only ever see a small part of what exists, and why that part is meant to shrink until it becomes nothing. The curtain is closing, the lights are turning off, and we are watching it happen in real time. Chapter 4, The Shrinking Horizon. There is a question that troubles every astronomer who thinks about the speeding up universe. How big is reality? Not the observable universe that we can measure. Not the region inside our event horizon that we can calculate, but the real, complete universe. All of it, every galaxy that exists anywhere, whether we can see it or not. The answer is both humbling and frightening. We do not know. The observable universe has a radius of about 46.5 billion light-years. This sounds like it should be the full size of everything that exists. It is not. It is only the distance light has had time to travel since the Big Bang. The universe is 13.8 billion years old, but the light we receive from the cosmic microwave background began its trip when the universe was only 380,000 years old, and has been traveling ever since while space itself expanded. The mix of travel time and expansion gives us our current horizon, but there is no reason to think the universe ends at that horizon. No reason at all. Imagine you are standing on a boat in the middle of the ocean. The horizon surrounds you in every direction, maybe 4 or 5 kilometers away. Beyond that horizon, the ocean continues. Ships, islands, continents, a whole world that you cannot see because Earth's curve blocks your view. Your visible horizon is not the edge of the ocean. It is only the edge of what you can see from where you are. The cosmic horizon works the same way. We sit at the center of a sphere of visibility set by the age of the universe and the speed of light. Beyond that sphere, the universe continues. Galaxies, clusters, superclusters, empty spaces, more cosmic webs stretching in every direction, maybe forever. Maybe with differences in structures we cannot imagine, maybe repeating patterns or unique arrangements or strange physics. We will never know. Light from those regions has not had enough time to reach us. Light from those regions may never reach us. They are beyond our horizon, hidden not just by distance, but by the limited speed of information and the limited age of time. Some cosmology models suggest the universe is finite, but has no edge, like the surface of a sphere. Travel far enough in any direction, and you would come back to where you started. In such a universe, the total size could be calculated, even if the number is huge. Other models suggest the universe is infinite, stretching forever with no edge, no border, no end. In an infinite universe, there would be infinite galaxies, infinite stars, infinite possibilities, infinite copies of everything that could exist. We cannot tell which idea is correct with today's observations. The universe appears flat to how accurately we can measure it. This means if it is curved, the curve is so small that the total size must be much larger than the observable part. Estimates suggest the full universe could be at least 250 times larger than what we can see. Maybe more, maybe endlessly more. This means that even right now, we are cut off from most of existence. Think about what that means. If the universe is 250 times larger than the observable region by volume, then we can see less than 0.5% of reality. Less than 0.5%. Everything we have ever seen, every galaxy we have ever photographed, every signal we have ever received is a tiny bubble of awareness floating in a shockingly huge ocean of unknown cosmos. And that bubble is shrinking. The expansion of space is not just pulling distant galaxies away from us. It is making the cosmic event horizon shrink compared to the cosmic web. Galaxies we can see today will shift red and disappear. Galaxies we can reach today will become unreachable. The light from the cosmic microwave background, already stretched from visible light to microwave light by nearly 14 billion years of expansion, will keep stretching until it becomes impossible to detect. Then nothing at all. In about 100 billion years from now, plus or minus a few tens of billions, the cosmic microwave background will have shifted beyond the ability of any possible technology to detect. It will still exist. The photons will still be moving through space, but their wavelength will be so huge, their energy so tiny that they will blend in with the random quantum noise of empty space itself. The echo of the Big Bang will go silent. In about 150 billion years, the last galaxies outside our local gravity-bound group will cross the event horizon. The sky will empty, not all at once, but slowly. Galaxies will fade, their light stretching red, then infrared, then microwave, then gone. One by one, the lights will turn off. Future astronomers will see the last outside galaxy fade below what they can detect and disappear into the expanding emptiness. And then what? The local group will remain. The Milky Way and Andromeda are held together by gravity and will merge in about 4 to 5 billion years, long before the outside galaxies vanish. The result, a giant elliptical galaxy often called Milkdromeda, will contain the combined stars and gas of both original galaxies. A few dozen smaller satellite galaxies will orbit this merged system. Together, this gravity-bound cluster will resist the expansion of space because the pull between its parts is stronger than the expansion at their short distances. But resist is not the same as defeat. Milkdromeda will be an island, a single huge galaxy surrounded by complete emptiness. No visible neighbors, no cosmic web, no sign that the universe ever had anything else. The stars will still shine for a while. New stars will still form from the gas and dust inside the merged galaxy for a while, but eventually the fuel will be used up. Star formation will stop. The stars that exist will burn through their nuclear fuel and die. The future beings of Milkdromda, if any exist, will study astronomy under conditions very different from ours today. They will have no redshift data from distant galaxies because there will be no distant galaxies to see. They will have no cosmic microwave background because it will have stretched beyond detection. They will have no way to measure the Hubble constant, the age of the universe, or the existence of dark energy. All the evidence that lets us figure out cosmology will have been erased by the same expansion that once allowed it to be seen. This is not guessing. This is physics. The math is clear. The results cannot be avoided. We live in a special time, a short moment on a cosmic scale, when the universe shows its structure to observers able to understand it. Before us, early civilizations had not yet appeared. After us, the evidence will be gone. We live in the sweet spot, the era when intelligent life can look at the cosmos and figure out its history, its makeup, its future. And what a future it is. The shrinking horizon is not just a loss of space. It is a loss of knowledge, a loss of connection, a loss of meaning in a very real way. Think about what it means to be cut off. Right now, there are galaxies we can see but can never reach. Their light comes to us, showing us their past, but any message we send will never arrive. If intelligent civilizations exist in those distant galaxies, we cannot talk to them. We cannot share information. We cannot share discoveries. We cannot even be sure they exist, except by guessing from statistics that say they probably exist somewhere in those billions of visible galaxies. In the future, as the horizon shrinks, the number of visible galaxies will drop. The number of civilizations we could ever contact will drop. The universe will feel lonelier by any measure we can use. And here is the deeper sadness. The universe was once more connected than it is today. Long ago, when the universe was younger and smaller, galaxies were closer together. The expansion was slower. The cosmic web was thicker. If intelligent civilizations had existed then, they would have had more neighbors within reach. Communication across cosmic distances would have been easier. Not easy, of course. The distances were still huge, but easier than today and much easier than tomorrow. We missed the window. Or rather, we arrived too late. By the time humans evolved, by the time we built technology able to see distant galaxies and think about interstellar communication, the expansion had already been speeding up for billions of years. Galaxies had already been moving apart for billions of years. The golden age of cosmic connection, if it ever existed, ended long before our sun formed, and the window keeps closing with every moment. This is why some scientists think the Fermi paradox, the question of why we have not found alien civilizations, might have a cosmological answer. Maybe the universe is naturally unfriendly to communication between intelligent species, not just because of distance, but because of expansion. Maybe civilizations appear, grow, and disappear before they can ever cross the gaps between them. Maybe the silence of the cosmos is not a mystery, but a rule built into the laws of reality. The emptiness speaks louder than any signal we have ever heard. But the shrinking horizon also brings questions that go beyond science. What does it mean for something to exist if we can never know about it? The galaxies beyond the event horizon still exist. Stars still burn there. Planets still circle those stars. If life exists in those far places, it keeps changing, struggling, and wondering about its place in the universe. But from our point of view, those places are gone. They have crossed beyond what matters to us. They cannot affect us. We cannot affect them. The cause and effect link that defines a relationship has been cut. Does it matter that they exist? Does anything beyond the horizon have meaning if it can never interact with anything inside the horizon? Physics cannot answer these questions, but physics forces us to ask them. The observable universe is not the universe. The reachable universe is not the observable universe. The connected universe is smaller still, and all of these are shrinking. In the next chapter, we will face another kind of cosmic isolation. The silence of space, the emptiness not just of matter, but of intelligence. The Fermi paradox and what it tells us about our place in a universe that seems, by every observation we have made, to be completely and frighteningly alone. We are not only isolated by distance, we are isolated by silence. Chapter 5, The Great Silence, summer of 1950, Los Alamos National Laboratory in New Mexico. 4 physicists walked to lunch, talking casually about flying saucers and the possibility of alien life. Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. The talk moves to other topics. Then suddenly, Fermi asks a question that will trouble science for generations. Where is everybody? The question was simple. The meaning was deep. If the universe is huge and old, if stars are common and planets are common, and the conditions for life are not extremely rare, then intelligent civilizations should have appeared many times throughout cosmic history. Some of those civilizations should have developed space travel. Some should have spread through their nearby stars, then their galaxies. Given millions or billions of years of extra time, some should have spread across the universe, leaving clear signs of their existence. We should see their megastructures. We should hear their signals. We should find their probes in our own solar system. We should have been contacted by now. We have not been contacted. We see no megastructures. We hear no signals. We find no probes. The universe looks, by every observation we have made, completely empty of intelligent life beyond Earth. This is the Fermi paradox, and it is one of the most troubling problems in all of science. Look at the numbers. The Milky Way galaxy has between 100 billion and 400 billion stars. The observable universe has at least 200 billion galaxies, maybe as many as 2 trillion. Each of those galaxies has hundreds of billions of stars. The total number of stars in the observable universe is about 10 to the power of 24. A trillion stars. More stars than grains of sand on all the beaches on Earth. Now think about time. The universe is 13.8 billion years old. Earth is only 4.5 billion years old. The Milky Way has stars that are over 10 billion years old. If Earth-like planets formed around those old stars, if life started on some of them, if intelligence evolved even a tiny part of the time it did on Earth, then there should be civilizations in our galaxy alone that had billions of years to develop technology before our solar system even existed. A civilization with a billion-year head start on humanity should be unbelievably advanced. They should have mastered interstellar travel, even if it is far slower than light. They should have spread across the galaxy, even at 1% the speed of light, even settling just one new star system every 1,000 years, even moving very slowly. A spacefaring civilization could fill the entire Milky Way in about 10 million years. That is less than 1% of the galaxy's age. Where are they? Decades of searching have found no solid proof of alien intelligence. The search for extraterrestrial intelligence, SETI, has checked millions of stars across many wavelengths for signals that might be artificial. Nothing. Studies have searched for megastructures, Dyson spheres, or star engineering that would change how stars shine in detectable ways. Nothing. Careful searches of our own solar system have found no alien objects, no probes, no signs of past visits, nothing. The silence is overwhelming, and it needs an explanation. Many ideas have been suggested. Maybe life is extremely rare. Maybe the jump from simple chemistry to self-copying molecules is so unlikely that it happened only once in the observable universe. We might be alone, not because the universe hates intelligence, but because we were first. This idea is sometimes called the rare Earth hypothesis, and it would explain the silence while placing humans in a very special position. Maybe intelligent life is common, but spacefaring civilizations are rare. Maybe there is a great filter, some obstacle that stops civilizations from reaching the stars. This filter could be behind us, meaning we already passed the hardest step and our future could be safer. Or it could be ahead of us, meaning we face extinction or stagnation before becoming a true interstellar species. Nuclear war, climate collapse, artificial intelligence disasters, running out of resources, self-destruction through technologies we have not yet invented. The great filter, if it is ahead of us, is an existential danger that destroyed every civilization before ours. Maybe advanced civilizations choose not to expand. Maybe at a certain stage, species turn inward instead of outward. Virtual worlds, life beyond biology, or deep philosophy that makes physical expansion feel meaningless. Maybe the universe is full of quiet civilizations that do not want to explore or communicate. This idea requires that every advanced civilization makes the same choice, which seems unlikely given how different human cultures already are. Maybe we are being avoided on purpose. The zoo hypothesis says advanced civilizations know about us, but choose not to contact us, watching from far away like scientists studying a primitive tribe. The dark forest hypothesis, made popular by the science fiction writer Liu Cixin, suggests the universe is dangerous and civilizations hide, because contact could mean destruction. In a universe where you cannot know another civilization's intentions, the safest choice is silence. Maybe the universe is simply too large and too empty for civilizations to ever find one another. The distances between stars are huge. The time scales involved in traveling between stars are enormous. Civilizations might rise and fall without ever meeting in time or space, like fireflies blinking in a forest at different moments, each believing it is alone. But there is another possibility, one that connects directly to the theme of this investigation. Perhaps the universe is becoming unfriendly to intelligence. Think about what we have learned about cosmic expansion. Galaxies are moving apart. The event horizon is shrinking. The observable universe is getting smaller. Every year, regions of space that were once possibly reachable become permanently cut off. The cosmic web is stretching thinner. The connections that would allow civilizations to find each other are being broken. Now imagine running this process backward in time. When the universe was younger, galaxies were closer together. The expansion rate was slower. The distances between possible homes for life were smaller. Communication across interstellar distances, while still hard, was slightly easier. The window for contact was wider. That window has been closing ever since dark energy began controlling the expansion about 5 billion years ago. And it will keep closing until no contact is possible at all. Perhaps civilizations have appeared throughout cosmic history, but always too far apart, always missing each other by gaps of millions of years or billions of light years. Perhaps the silence is not proof that we are alone, but proof that the universe is built to keep intelligent species separated from each other. Perhaps the void is not just empty of matter, but empty of the connections that would allow awareness to recognize itself across cosmic distances. This is a dark idea, but it matches the physics. There is also the problem of time. Human civilization has existed for about 10,000 years. We have had radio technology for only a century. We have been actively searching for signals from other civilizations for only about 6 decades. If intelligent civilizations have an average technological lifespan of about 10,000 years before they destroy themselves or change beyond our ability to recognize them, and if such civilizations appear randomly across cosmic history, then the chance that 2 civilizations would overlap in time and space and technology is extremely small. The universe has been able to support life for at least 10 billion years. It will continue to support life, at least on some worlds, for trillions of years to come. Human civilization exists in an incredibly tiny slice of that time. The chances that another civilization's 10,000-year window would overlap with ours in a galaxy where star systems are separated by light years and signals take generations to travel, even between neighbors, are extremely low. We might be shouting into a cosmic forest where all the other voices have already gone silent and the future voices have not yet begun. And the silence might be permanent. As expansion speeds up, as galaxies drift beyond the event horizon, as the reachable universe shrinks, the chances for contact will fade. Future civilizations that arise in the merged remains of the local group will have even fewer possible neighbors. They will inherit a universe that shows no sign of its former richness. No clues that the sky once held trillions of galaxies. No reason to think intelligence might exist anywhere else. The silence of the cosmos is not just confusing, it is prophetic. It predicts the silence that waits for all intelligence in the far future, when expansion has torn the cosmic web apart and every pocket of matter drifts alone through endless emptiness. Perhaps the most troubling part of the Fermi paradox is what it suggests about our own future. If advanced civilizations always fail to spread across the universe, if the great filter lies ahead instead of behind us, then our future is bleak. Every civilization that reaches our level of development seems to fail to reach the stars. Something stops them. Something will stop us. Unless we are the exception, unless we are the first, unless the great filter is behind us and the path ahead is open. But even if we are the exception, even if we somehow become a truly interstellar species, we cannot escape expansion. We cannot outrun the void. We can spread through our local group. Perhaps we can survive for trillions of years among the merged remains of nearby galaxies, but we will still be isolated. We will still drift alone through an expanding emptiness. We will still inherit a universe where the lights go out one by one until nothing remains. The silence of space is not temporary. It is the natural state of an accelerating universe. It is the destination toward which all existence is moving, and we are already on that path. This ends the first half of our investigation. In the remaining chapters, we will explore why escape is impossible, how the last stars will die, what happens to matter itself in the far future, where consciousness might survive in a dead universe, and why the void is not just the absence of everything, but the active consumption of everything. The story grows darker from here, but the darkest chapters hold the deepest truths. Chapter 6, The Impossible Journey. There is a dream that has followed humanity since we first looked at the stars, the dream of reaching them. Science fiction has fueled this dream for generations with ideas of warp drives and hyperspace, and faster-than-light travel that would shrink cosmic distances into manageable trips. We imagine ourselves spreading across the galaxy, settling new worlds, meeting alien civilizations, becoming a species that fills the stars. It is a beautiful dream. It is almost certainly impossible, not hard, not expensive, not challenging, impossible. The physics of traveling between stars presents barriers so basic, so unbeatable that no technology we can imagine can overcome them. The emptiness between stars is not just a distance to cross. It is a wall built into the structure of reality itself. Start with the simplest problem, distance. The nearest star to our sun is Proxima Centauri, a small red dwarf about 4.24 light-years away. That sounds close when you say it fast. 4 years at the speed of light. But nothing we build moves at the speed of light. The fastest spacecraft humans have ever launched is the Parker Solar Probe, which reached speeds of about 630,000 kilometers per hour as it flew close to the sun. At that speed, the trip to Proxima Centauri would take about 7,000 years. 7,000 years. That is longer than all recorded human history. Civilizations have risen and fallen in less time. Languages have changed beyond recognition. Entire species have disappeared. A spacecraft launched today at the fastest speed we have ever achieved would arrive at the nearest star when the descendants of our descendants have forgotten we ever existed. And Proxima Centauri is the nearest star. Most stars in the Milky Way are thousands of light-years away. The center of our galaxy is about 26,000 light-years away. The nearest large galaxy, Andromeda, is 2.5 million light-years from here. The edge of the observable universe is 46 billion light-years away. The distances are not just big. They are impossible to truly understand. But maybe we could travel faster, much faster. Maybe with advanced engines, we could reach a large fraction of the speed of light and shorten trips to decades or centuries instead of thousands of years. This is where physics becomes cruel. The energy needed to push a spacecraft to relativistic speeds, speeds close to the speed of light, is beyond imagination. Einstein's equation E equals mc squared tells us that mass and energy are the same thing. As an object moves closer to the speed of light, its effective mass increases. More mass means more energy is needed to speed up more. The relationship is not straight, it is exponential. The closer you get to light speed, the more energy you need, and the gains shrink toward infinity as you approach that final limit. To speed up a spacecraft with the mass of a small car to 90% of the speed of light would need energy equal to about 100 times the yearly energy use of all human civilization. For a spacecraft big enough to carry humans with life support and supplies, the energy needs grow by huge amounts. We are talking about energy levels greater than the total output of the sun for long periods of time. And that is only to speed up. You also have to slow down when you arrive. Unless you plan to rush past your destination at near light speed without stopping, you need about the same amount of energy to slow down as you used to speed up. Double the already impossible energy demand. What fuel could give that much energy? Chemical rockets are useless. They give too little energy for their mass. Even nuclear fission, which powered atomic bombs, falls short by many orders of magnitude. Nuclear fusion, the process that powers the sun, comes closer, but still needs fuel amounts that would make the spacecraft far too heavy. The only fuel that could theoretically give enough energy is antimatter, where matter and antimatter destroy each other and turn 100% of mass into energy. Antimatter is real. We have made it in particle accelerators. We have studied it. We understand how it works. We have produced a total of about 20 nanograms of antimatter in all of human history, 20 billionths of a gram. At today's production rates and costs, making enough antimatter to power a starship would require more resources than humanity has ever used on any project by millions or billions of times. And there are more problems. At near light speeds, even the emptiest parts of interstellar space become deadly. The space between stars is not perfectly empty. It has about 1 atom per cubic centimeter on average, mostly hydrogen. When standing still, these atoms are harmless. At 90% of the speed of light, they become deadly. A spacecraft moving that fast would be hit by these atoms, which would strike the hull with energies like those in powerful particle accelerators. The impacts would create radiation. They would wear away the hull. They would cook the crew with deadly gamma rays. To protect against this radiation would require thick shielding that would make the energy needs even more impossible. To push the particles away with magnetic fields would need huge amounts of energy for the entire trip. There is no easy answer. Every solution turns one impossible problem into another. Cosmic rays cause similar problems. These high-energy particles from distant supernovae and other cosmic events fill all of space. On Earth, our atmosphere and magnetic field protect us from the worst of them. A spacecraft in interstellar space would have no such protection. Over trips lasting decades or centuries, the total radiation dose would be deadly many times over. Maybe humans could not make the trip, but machines could. Robotic probes do not need air or food. They do not get cancer from radiation. They can be smaller and lighter, lowering energy needs. Projects like Breakthrough Starshot suggest sending tiny probes, spacecraft weighing grams, pushed by powerful lasers from Earth toward nearby stars at speeds of about 20% of the speed of light. Even this idea faces huge problems. At 20% light speed, a tiny grain of dust becomes a bullet that could destroy the probe. The laser system needed to push these probes would have to be thousands of times stronger than any laser ever built. The probes would be so small that carrying useful scientific tools would be very hard. And even if they worked, they would reach Proxima Centauri with no way to slow down, rushing past at 20% of the speed of light, snapping a few blurry pictures before flying off into the void. The laws of physics do not care about our dreams. But even if we could solve all these problems, even if we somehow built technology that let us travel between stars at reasonable speeds, we would still face the final barrier, the expansion of space. Remember what we learned earlier. The universe is expanding. Faraway galaxies are moving away from us faster than the speed of light. The cosmic event horizon marks the line beyond which no contact is possible. No matter how fast we travel, even at light speed, we could never reach galaxies beyond that. Horizon, and the horizon is coming closer. Every year, galaxies that were once possibly reachable cross that line. The amount of space we could ever visit is shrinking. Even with perfect technology, even if we could travel at light speed without using infinite energy, the universe would still be closing doors faster than we could open them. We are trapped not by technology, not by our limits as a species, but by the laws of reality itself. The distances are too great. The energy demands are too extreme. The dangers are too deadly. And expansion makes sure that even our best efforts would reach only a smaller and smaller part of what exists. This is why some scientists think the Fermi paradox may have a simple answer. Maybe no civilization ever manages interstellar travel because interstellar travel is impossible. Not just hard, but physically impossible, built into the laws that control reality. Maybe every intelligent species reaches the same conclusion we are reaching now. The stars are visible. The stars are unreachable. The space between them is an uncrossable gap that guarantees permanent isolation. Think about what this means for the future of intelligent life. If we cannot reach other star systems, we are limited to our own solar system for as long as we exist. When the sun grows into a red giant in about 5 billion years, we must either build technology to survive it, move to outer planets or moons, or die. When the sun becomes a white dwarf and slowly cools, we must find new energy sources or die. When the last nuclear fuel in our solar system is used up, we must accept darkness or die. There is no escape plan, no backup option that involves moving to another star, no rescue among distant worlds. The stars are not stops on a journey we have not started yet. They are lighthouses on a shore we can never reach. They show us our isolation without offering help. And what about the civilizations that might live around those distant stars? They face the same limits we do. They cannot reach us any more than we can reach them. The void makes sure that every intelligence in the universe, if others exist, grows, changes, and ends in isolation. Like ships passing in the night that never come close enough to call out. The universe is not a community waiting to connect. It is a group of islands separated by oceans that cannot be crossed. The space between stars is not an engineering problem. It is a basic rule of existence. Some people hope that strange new physics might offer a way around these limits. Wormholes, warp drives, shortcuts through extra dimensions. These ideas appear in equations from relativity and quantum mechanics. tempting hints that space might be bent or stretched or skipped in ways that make star travel possible. But careful study of these ideas always shows impossible demands. Wormholes, if they can even exist, would need exotic matter with negative energy that may not exist. Warp drives would need similar exotic matter in amounts greater than the mass of the Sun. Extra-dimensional travel, even if real, would need energy that makes near-light speed travel look easy by comparison. There is no free answer. Physics gives no escape from the rule of distance. The dream of reaching the stars is just that, a dream. Beautiful, inspiring, a sign of human imagination and hope, but still a dream. The void stands between us and every star we see, vast and cold and completely uncaring about our wishes. In the next chapter, we will explore what happens to those distant stars over cosmic time, how they will use up their fuel, how the universe will slowly grow dark, how the age of light is only a brief spark in an endless darkness. The stars we cannot reach will not last forever. Nothing lasts. Chapter 7. The Death of Light. The universe is 13.8 billion years old. The last star will die in about 100 trillion years. That means we exist in the first 110,000th of 1% of the universe's timeline when stars shine. The age of light, the time when the universe glows with nuclear fusion, is a brief spark between the darkness before and the much longer darkness after. We are seeing the universe at its brightest, and that brightness is fading. To understand how stars will die, we must first understand how they live. A star is a balance between two opposing forces. Gravity pulls inward, trying to crush the star into a single point. Radiation pressure pushes outward. This pressure is made by nuclear fusion reactions in the star's core. These reactions turn hydrogen into helium and release huge amounts of energy. As long as fusion continues, the outward push balances the inward pull. The star stays stable. The light continues to shine, but fusion needs fuel. The hydrogen in the star's core is slowly used up. It is changed into helium and heavier elements. When the hydrogen runs out, the balance breaks. Gravity wins, the core shrinks, the outer layers expand. The star enters a new stage of its life, one that leads toward death. The way a star dies depends on its mass. Stars like our Sun, medium-mass stars, will grow into red giants when their core hydrogen is gone. The outer layers will swell outward, swallowing the inner planets. Mercury will be destroyed. Venus will be destroyed. Earth may be destroyed or may survive as a burned, lifeless rock orbiting near the edge of the giant star. The core will keep shrinking until it becomes hot enough to fuse helium into carbon and oxygen. This gives the star some extra time, maybe a few 100 million years. But eventually the helium is also used up. The core cannot go further. The fusion reactions stop. What is left is a white dwarf. A dead star about the size of Earth, but with the mass of the Sun. Extremely dense. A teaspoon of white dwarf material would weigh several tons. At first it is hot, glowing with leftover heat from its earlier life. But with no fusion to replace the energy, the white dwarf slowly cools. Over billions of years, it releases its heat into space, growing dimmer and dimmer until it becomes a black dwarf. A cold, dark, dead ball of dense matter drifting through empty space. No black dwarf has ever formed yet in the universe. The cooling takes longer than the current age of the cosmos. But given enough time, every white dwarf will become one. Bigger stars die in more violent ways. Stars several times heavier than the Sun can fuse elements beyond helium. Carbon, oxygen, neon, magnesium, silicon, all the way up to iron. But iron is the final step. Fusing iron does not release energy, it uses energy. When the core of a massive star fills with iron, fusion suddenly stops. The core collapses in a fraction of a second. The outer layers, now unsupported, fall inward at speeds close to 1/4 the speed of light. They crash into the collapsing core and bounce back, creating a shock wave that rips the star apart. This is a supernova. For a few weeks, one dying star can shine brighter than an entire galaxy. The explosion spreads heavy elements through space, planting future stars and planets with the materials that will later form rocky worlds and living things. Every atom of iron in your blood, every atom of calcium in your bones, every atom heavier than helium was made in the core of a massive star and spread by a supernova explosion billions of years ago. What remains after a supernova depends on the mass of the original star. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star, an object so dense that protons and electrons are squeezed together into neutrons. A neutron star packs the mass of the sun into a sphere about 20 kilometers wide. A teaspoon of neutron star material would weigh hundreds of millions of tons. If the core is heavier than about 3 solar masses, nothing can stop the collapse. The core keeps falling inward, squeezing itself into smaller and smaller space until it disappears behind an event horizon and becomes a black hole. A region of space where gravity is so strong that nothing, not even light, can escape. These are the endings of stars. Red giants turning into white dwarfs and then black dwarfs. Supernovae leaving behind neutron stars or black holes. And the smallest stars, red dwarfs, following their own slow path toward darkness. Red dwarfs are the most common stars in the universe, making up about 70% of all stars. They are small, usually less than half the mass of the sun. They are cool, glowing, dim red instead of the bright yellow-white light of larger stars. And they live for an extremely long time. Because red dwarfs are fully mixed inside, constantly blending the material in their cores with the material in their outer layers, they can burn much more of their hydrogen than larger stars. Because they burn this fuel slowly, they can keep shining for trillions of years. The smallest red dwarfs, just massive enough to keep fusion going, might live for 10 trillion years or more. They will be the last stars shining in the universe. But in the end, even red dwarfs will use up their fuel. The final ones will burn out about 100 trillion years from now. When that last red dwarf fades and dies, the age of stars will end. The stelliferous era, the time when the universe is full of starlight, will give way to the degenerate era, when the only remaining stellar objects are the remains of dead stars. Imagine the universe at that future time. The cosmic microwave background has long faded beyond detection. Distant galaxies crossed the event horizon tens of billions of years earlier. The sky has no outside objects, only the merged remnant of the local group, one giant galaxy that was once the Milky Way and Andromeda, along with dozens of smaller companions. And that galaxy is dying. The stars that once lit its spiral arms have all burned out. The galaxy is filled with dark objects. Black dwarfs, the cooled remains of sun-like stars. Neutron stars slowly spinning down as their magnetic fields fade. Black holes hiding in the darkness, sometimes swallowing matter that wanders too close. Brown dwarfs, failed stars that never started fusion, drifting cold and silent. Planets torn from their parent stars, frozen solid, wandering alone through space. The only light comes from rare events. Sometimes two brown dwarfs may crash together and merge, briefly starting fusion in the combined mass and forming a temporary star that shines for a few billion years before running out of fuel. Sometimes matter falling into a black hole releases energy before crossing the event horizon, creating a short flare. Sometimes a white dwarf in a pair of stars gathers enough mass to trigger a thermonuclear explosion, a type of supernova that lights up the dead galaxy for a few weeks. But these events are rare. The galaxy grows darker with each passing age. The small flashes of light become farther apart, weaker, and more lost in the endless darkness. Any civilization that exists in this time faces challenges we can hardly imagine. Energy is rare. The easy fuel of hydrogen fusion is gone. Whatever intelligence survives must find ways to get energy from the dense remains of dead stars, from the spin of neutron stars, from the gravity of black holes. Every tiny bit of energy is more valuable than we can imagine. Freeman Dyson, the physicist who imagined giant spheres collecting energy from stars, also imagined what intelligent life might do in this dying universe. He suggested that civilizations could slow down their thinking, having one thought every million years instead of every second, stretching their experience across the huge time scales of the degenerate era. By thinking slowly and using little energy, they might last for incredibly long times, experiencing billions of years of thought, even as the universe around them becomes emptier and colder. But even this idea has limits. The universe keeps expanding. Dark energy continues to stretch space, pushing objects farther apart and increasing isolation. Eventually, even the merged galaxy will break apart, its pieces drifting away into empty space, each dead star becoming alone. And eventually, even these remains will decay. In the next chapter, we will look at this long decay, how protons may fall apart, how black holes will evaporate, how matter itself will change into radiation. The degenerate era is not the end. It is only the beginning of an even longer era of emptiness. The death of light is only the start of the final darkness. Chapter 8, The Long Decay. After the last star dies, the universe will still contain matter, huge amounts of it. Black dwarfs and neutron stars and black holes, planets and asteroids and debris, the parts of atoms, protons and neutrons and electrons spread through the cooling cosmos. But matter does not last forever. Given enough time, everything breaks apart. This is the era of the long decay, and the numbers involved are so large they are hard to understand. First, consider the fate of ordinary matter. According to our best theories of particle physics, protons are stable. A proton alone should stay a proton forever. This is what the standard model of particle physics predicts. But the standard model is not complete. We know it cannot explain everything. Gravity is missing. Dark matter is not explained. Dark energy is still a mystery. New theories that try to unite all forces predict that protons are not truly stable. They just last for an extremely long time. How long? Grand unified theories say protons decay with a half-life of about 10 to the power of 34 years. That is a 1 followed by 34 zeros. To compare, the universe today is about 10 to the power of 10 years old. The predicted proton lifetime is a trillion times longer than the universe has existed so far. We have looked for proton decay in deep underground experiments, watching huge tanks of water for the small flash of radiation that would show a proton breaking apart. We have not seen it yet. Our experiments can rule out half-lives shorter than about 10 to the power of 34 years, which is exactly where the theories expect decay to happen. We may be close to finding it, or it may last even longer, or protons may truly be stable. But suppose proton decay is real. What happens over times of 10 to the power of 34 to 10 to the power of 40 years? The protons in every atom in the universe will decay. A proton turns into a positron, the antimatter partner of an electron, and a neutral pion. The pion quickly breaks down into gamma-ray light. The positron later meets an electron. The two destroy each other and more gamma rays appear. The final result is radiation, pure energy spreading through expanding space. Every black dwarf, every neutron star, every planet, every asteroid, every grain of dust will slowly disappear, not by exploding or collapsing, but by fading away particle by particle, atom by atom. The matter that once formed stars and worlds will turn into radiation. The process is extremely slow by human standards, but it cannot be stopped. Given enough time, nothing solid will remain. Imagine the universe at this time, 10 to the power of 40 years after the Big Bang. The stars have been dead for almost all of that time. The black dwarfs have been cooling for nearly as long. And now they are breaking apart, their atoms falling apart, their mass turning into weak radiation that spreads into empty space. A black dwarf losing mass through proton decay produces about 400 watts of power. 400 watts, enough to run a few light bulbs, from an object with the mass of the sun. This is the energy of a dead star slowly fading over time scales longer than anything you can imagine. But proton decay, if it happens, is not the end. Some objects last longer. Black holes. A black hole is not made of matter in the usual way. It is a region of spacetime curved so strongly that nothing, not even light, can escape past its event horizon. The matter that formed the black hole has been crushed away, leaving only mass, charge, and spin stored in the shape of space itself. For many years, scientists believed black holes would last forever. Once formed, they would stay forever, growing as they swallowed matter, but never shrinking or fading, symbols of unstoppable gravity. Then Stephen Hawking showed this was wrong. In 1974, Hawking proved that black holes give off radiation. This Hawking radiation comes from quantum effects near the event horizon, where pairs of tiny particles appear, and sometimes one falls in while the other escapes. The escaping particle carries energy away. That energy comes from the black hole. The black hole loses mass. This process is very slow. A black hole with the mass of the sun would need about 10 to the power of 67 years to fully disappear. A supermassive black hole with 1 billion times the sun's mass would need about 10 to the power of 100 years. That is a Google years, a 1 followed by 100 zeros. These times are so huge they make proton decay seem fast, but they are still not endless. Given enough time, every black hole will fade away. As a black hole loses mass, it becomes smaller. As it becomes smaller, it gets hotter. As it gets hotter, it releases energy faster. The process speeds up. At the end, a black hole shrinks very quickly and releases a burst of radiation before disappearing completely. What is left after all black holes are gone? Almost nothing. The universe at this time, 10 to the power of 100 years and beyond, contains only basic particles: electrons, positrons, photons, neutrinos, and maybe dark matter particles. If dark matter is stable, these particles drift through space that has expanded to unbelievable size. The average distance between particles may be larger than today's observable universe. Each particle is completely alone, drifting through emptiness, only rarely meeting another particle over enormous times. Even these rare meetings matter. An electron and a positron may meet and destroy each other, turning into light. Photons keep stretching as space expands, becoming longer and longer waves, losing energy, cooling toward absolute zero, but never quite reaching it. The universe moves toward its final state: maximum entropy, full balance, heat death. Entropy measures disorder, how many ways something can exist while looking the same. The second law of thermodynamics says entropy in a closed system always increases or stays the same. It never decreases on its own. Order turns into disorder. Structure spreads into sameness. Hot things cool, cold things warm, until everything reaches the same temperature. The universe is closed in this way. There is nothing outside it to trade energy with. Over time, entropy grows. Stars turn ordered fuel into scattered light. Black holes mix information. Particles spread farther and farther apart. The universe moves toward maximum entropy, where no change is possible because there are no differences left to cause change. At heat death, the universe is a smooth spread of particles at the same temperature, just above absolute zero. Nothing happens because nothing can happen. All processes are finished. The universe has reached full balance. But this may still not be the end. Some ideas say the vacuum of space is unstable. The Higgs field that gives particles mass may not be in its lowest energy state. It may be a false vacuum that could suddenly change to a lower energy state. If that happens, a bubble of true vacuum would form and expand at the speed of light, changing everything it touches. Inside that bubble, atoms as we know them might not exist. Life would be impossible. The bubble would sweep through the universe, erasing everything and replacing today's physics with something new. This is called vacuum decay. While the chance of it happening at any moment is tiny, over times of 10 to the power of hundreds of years, even very rare events can occur. The universe may not slowly fade into heat death. It may instead be erased by a sudden change that rewrites the laws of physics. Or there could be a big rip. If dark energy grows stronger over time, space may stretch so fast that it tears apart galaxies, then stars, then planets, then atoms, and finally space itself. Everything would be pulled apart into endless expansion. We do not know which ending will happen: heat death, vacuum decay, or the big rip. Maybe none of these, maybe something even stranger that our science cannot yet imagine. But all endings share one idea. The void wins, matter decays, energy spreads out, structure falls apart. The universe slowly moves toward emptiness, toward sameness, toward a state where nothing exists as we know it. This long decay is not a fight we can win. It is not a problem we can fix. It is the arrow of time pointing toward breakdown, the basic tendency of reality to simplify itself into nothing. In the next chapter, we will ask whether consciousness can survive in such a universe, whether minds can last through this long decay, whether awareness itself has a limit. The answer is disturbing. Chapter 9. The mind at the end of time in the far future, when the stars have burned out and matter has broken down and the universe has cooled to just a tiny bit above absolute zero. Is consciousness still possible? Can minds survive through the long darkness? Can awareness exist in a universe that has settled into thermal balance? These questions sit at the crossroads of physics, philosophy, and the deepest mysteries of existence, and they lead us to one of the strangest ideas in modern cosmology: the Boltzmann brain. Ludwig Boltzmann was an Austrian physicist who lived in the 19th century. He helped create the field of statistical mechanics, which explains how the behavior of huge numbers of particles creates the properties we see in large-scale matter, like temperature and pressure. Boltzmann understood that entropy, a measure of disorder, usually increases over time. He understood that the universe seems to have begun in a low-entropy state and is moving toward higher entropy. But this caused a problem. If the universe naturally moves toward maximum entropy, toward sameness and disorder, why do we see so much structure? Why do stars exist? Why do galaxies exist? Why do complex beings like humans exist? These are all low-entropy arrangements, islands of order in a sea of chaos. Boltzmann suggested a bold answer. Maybe the universe has already reached maximum entropy. Maybe the cosmos we see is only a fluctuation, a random pocket of low entropy that appeared by chance out of an endless sea of equilibrium. If you wait long enough in a universe at thermal equilibrium, random fluctuations will sometimes create regions of lower entropy. Most of these will be small and short-lived. But with infinite time, even very large fluctuations can happen. Stars, galaxies, observers. This idea was mostly forgotten for about 100 years. Then modern cosmologists brought it back in a disturbing way. Imagine a universe that has reached heat death. Particles float through huge empty space, rarely interacting, usually not at all. The temperature is the same everywhere, just barely above absolute zero. Entropy is at its highest possible value. Nothing interesting happens. But quantum mechanics says nothing is ever completely still. Virtual particles appear and disappear. Fields constantly shift. There is always a tiny chance that random arrangements will form on their own. Given enough time, a fluctuation could create anything, even a brain. A Boltzmann brain is a hypothetical self-aware being that forms spontaneously from random quantum fluctuations. It would appear suddenly, complete with fake memories of a life it never lived, observations of a universe that does not exist, beliefs about a past that never happened. It would exist for only a short moment, maybe just long enough to think one thought, before breaking apart back into the thermal balance from which it came. This sounds like science fiction, but the physics is simple. If the universe lasts long enough in a state of thermal equilibrium, the creation of Boltzmann brains is not just possible but unavoidable. Random fluctuations will eventually create every possible arrangement of matter, including arrangements that count as conscious observers. Here is the disturbing result. In a universe that lasts forever at thermal equilibrium, Boltzmann brains would greatly outnumber normal observers like us. For every human who evolved naturally on a planet orbiting a star, there would be countless trillions of Boltzmann brains that randomly appeared in empty space. By pure probability, if you are a conscious observer in such a universe, you are almost certainly a Boltzmann brain instead of a normal result of cosmic evolution. But you do not seem to be a Boltzmann brain. Your memories fit together. Your observations match what physics predicts. The universe you see looks like it has a real history going back 13.8 billion years. Either you are a normal observer in a young universe that has not yet reached equilibrium, or you are a Boltzmann brain whose fake memories happen to perfectly agree by an incredible coincidence. The first option seems far more reasonable, which means the universe probably does not last forever at thermal equilibrium. Something must stop Boltzmann brains from forming. Maybe vacuum decay destroys the universe before it reaches equilibrium. Maybe the expansion of space spreads everything out so much that even Boltzmann brains cannot form. Maybe our understanding of quantum fluctuations is incomplete. But the Boltzmann brain paradox points to a deeper question about consciousness in the far future. If minds need matter and matter is breaking down, then consciousness must someday end. The neurons in your brain work using electrical and chemical signals. The calculations that make up your thoughts need energy. Right now, that energy ultimately comes from the sun, which gets its energy from nuclear fusion. But when the stars die, when protons decay, when black holes evaporate, there will be no more concentrated sources of energy. The universe will be in thermal equilibrium. No differences, no contrasts, no imbalance to use. Thinking is thermodynamically costly. Every thought you have increases the universe's entropy, releasing waste heat into the surroundings. In a universe at maximum entropy, there is no surrounding space left to absorb waste heat. Computation becomes impossible. Consciousness, if it depends on computation, becomes impossible. This is the final limit not just for human consciousness, not just for biological life, but for any kind of awareness we can imagine. Minds need energy differences. The universe is destroying all energy differences. Therefore, minds cannot last forever. Some people have suggested ways around this limit. Freeman Dyson proposed that civilizations could survive by slowing down their thinking less often as the universe cools, stretching their inner experience across huge spans of time. In theory, a civilization using very little power could last for an extremely long time, experiencing many inner ages even as the outside universe slowly moves toward equilibrium. But this idea has limits. The universe is not only cooling, it is expanding. Objects are moving farther apart. The materials needed for computation are spreading out. Even if you could slow down enough to survive the cold, you would eventually face the problem of collecting the matter and energy needed to keep yourself going across ever-increasing distances. and quantum mechanics sets a limit on how slow you can be. There is a minimum amount of energy needed to flip one bit of information, set by the temperature of the environment. As the universe cools, this minimum gets smaller, but it never becomes zero. Eventually, the energy needed to support even the slowest possible computation will be more than what exists. Consciousness needs a physical base. A physical base needs energy. Energy needs imbalance. The universe is removing imbalance, so consciousness has a deadline. We do not know when that deadline is. It could be 10 to the power of 100 years after black holes evaporate. It could be sooner when matter is too spread out for focused computation. It could be later if we have missed some trick that lets minds survive extreme conditions. But the deadline exists. This may be the deepest meaning of the void. Not just that the universe is empty and becoming emptier. Not just that stars will die and matter will decay, but that awareness itself has a limit. The light of consciousness, like the light of stars, is temporary. It came from nothing, shines for a short time against the darkness, and will eventually fade back into nothing. There is a strange comfort in the Boltzmann brain idea, twisted as it is. Even after the deadline, even after organized consciousness is no longer possible, random fluctuations will sometimes create tiny flashes of awareness. Minds will appear, experience a single moment, and disappear. These minds will have no past and no future. They will be isolated points of experience in an endless nothing, but they will exist. Briefly, randomly, without meaning, they will exist. Is that comforting or terrifying? Maybe it depends on what you think consciousness is for. If consciousness exists to accomplish things, to build and create and connect, then the far future is unbelievably bleak. Nothing built will last. Nothing created will remain. Every connection will be broken by the expansion of space. If consciousness exists simply to experience, to observe, to be aware no matter the outcome, then maybe the brief flicker of Boltzmann brains is enough. The universe will still contain moments of experience, even if they are rare and disconnected. Awareness will never fully disappear, only become extremely uncommon. But there is a deeper question we have been circling, one that the physics of the void forces us to face. What is consciousness for in a universe that ends? We will explore this in the final chapter, The Final Isolation, the end of everything. Chapter 10, The Final Isolation. We started this journey by looking up at the night sky and realizing we were looking at almost nothing. We traced the empty spaces that dominate the cosmic web. We studied the force pulling galaxies apart. We watched the horizon shrink and the silence grow. We faced the impossibility of escape and the death of stars. We followed matter through its long decay and asked whether consciousness could survive. Now we have reached the end. Not the end of the universe, which may never truly end in the usual sense, but the end of everything that matters. The end of structure, the end of change, the end of story. The void wins. This is not a metaphor. It is not a philosophical opinion. It is the simple prediction of our best physics. The universe began in a state of extreme order, extreme density, extreme heat. It has been running down ever since. Entropy increases. Differences fade. Contrasts flatten out. The cosmos slowly moves toward sameness, toward balance, toward the absence of anything we would call interesting or meaningful or alive. The void is not just empty space waiting to be filled. It is an active process that eats everything. Every star that dies increases the power of the void. Every galaxy that passes beyond the cosmic horizon extends the void's reach. Every proton that decays turns a little more matter into a little more nothing. The void grows. The void advances. The void conquers, and we are already victims. Right now, as you read these words, galaxies are disappearing beyond the cosmic horizon at a rate of about 20,000 per second. That is not a mistake. 20,000 galaxies every second, each holding hundreds of billions of stars, slipping beyond any possible contact. By the time you finish this sentence, another 100,000 galaxies have become unreachable. By the time you finish this chapter, millions more. This is not something that will happen far in the future. It is happening now. It has been happening for billions of years. It will keep happening faster and faster until nothing is left within reach except our own small pocket of gravity-bound matter. We live in a short moment of cosmic time when the universe can still be seen by observers. The stars still shine. The cosmic microwave background is still detectable. Distant galaxies are still visible. We can look out at the universe and figure out its history, its makeup, its future. We can understand what we are, where we came from, and where everything is going. Future observers will not have this chance. The evidence will be gone. The cosmic microwave background will have stretched into undetectable noise. Distant galaxies will have disappeared beyond the horizon. Future astronomers, if any exist, will inherit a universe that looks still, lonely, and eternal. They will have no way to discover the Big Bang, no way to measure the expansion, no reason to think the universe was ever anything other than a single old galaxy drifting in endless emptiness. We are the fortunate ones. We see the whole picture. We understand, even if only faintly, the true size of what exists and what is being lost. And what we see is frightening. The universe is not made to last forever. It is not built to preserve meaning. It is not shaped to save anything we value. The laws of physics push everything toward breakdown, toward spreading out, toward the cold, dark balance where nothing happens because nothing can happen. Every civilization that has ever existed or ever will exist faces the same end. Every monument falls apart, every record fades, every memory disappears. The greatest achievements of any species, the deepest discoveries, the most beautiful creations, will all be erased by the long decay. In 10 to the power of 100 years, there will be no sign that anything ever mattered to anyone anywhere. This is not negativity. This is physics, but it is not the full story. Think about what it means that we exist at all. The universe spent 10 billion years getting ready for us. Generations of stars lived and died, creating the heavy elements that make planets and people possible. Galaxies formed and changed. Countless conditions had to line up. Countless unlikely events had to happen for consciousness to appear on at least one world. And here we are, aware, asking questions, understanding even imperfectly our place in the universe. The fact that consciousness exists at all in a universe that seems designed to erase it is amazing. The fact that we can understand the void, track its growth, and predict its victory is astonishing. We are the universe looking at itself, the cosmos becoming aware of its own nature and its own future. This awareness is temporary. It came from nothing and will return to nothing. But it is not nothing right now. Right now, in this moment, consciousness exists. Minds are thinking, questions are being asked, answers are being searched for. The void will consume everything, but it has not consumed everything yet. This is the strange gift of the present moment. We live in the narrow space between too early and too late. Before us, there was no one to witness the universe. After us, the evidence will vanish and the witnesses will be gone. We stand at the one moment in cosmic history where understanding is possible. What do we do with this understanding? Maybe nothing. The universe does not care what we do. Expansion will continue anyway. Stars will die anyway. Matter will decay anyway. Our actions, good or bad, will leave no lasting mark on a universe that erases all marks. But maybe that is not the point. Maybe the value of life is not how long it lasts, but how it feels. Maybe the meaning of consciousness is not what it accomplishes, but what it experiences. Maybe the importance of understanding is not whether it lasts forever, but whether it happens at all. The void is huge. The void is growing. The void will win. But the void is not here yet, not fully, not in this moment. Right now, stars are shining, galaxies are turning, planets are circling. Life is struggling, creating, and wondering. Minds are thinking about the infinite. Hearts are breaking and healing. Stories are being told. The universe is not dead. It is dying, yes, but dying is not the same as dead. There is still time, there is still experience, there is still meaning. Whatever meaning we choose to create, the isolation is coming. It is already starting, but it is not finished. We appear to be alone in the universe as far as we can tell. No messages from other civilizations, no visitors from distant worlds. The silence is huge and getting bigger, but we are not alone with each other. Not yet. Humanity shares a planet, shares a moment, shares an understanding of who we are and where we are headed. We are the universe's way of knowing itself before that knowing ends. We are the cosmos's brief flame of awareness before the final darkness. The void created us. The void will take us back. In between, we shine. That is not nothing. That is everything. The universe is 99% empty. It becomes emptier every second. Galaxies are slipping beyond reach. Stars are dying, matter is breaking down, consciousness is temporary. And yet here we are, aware of the void, thinking about the infinite, existing, however briefly, in defiance of the emptiness that surrounds us in every direction and every future we can predict. The void is not just empty space. It is an active force that consumes everything. But we are not nothing, not yet. And for now, for this moment, for this brief spark between the birth of the universe and its final heat death, that is enough. The void wins in the end. But the end is not here yet. And until it arrives, the universe contains at least one thing that matters. Us watching, understanding, existing. This is the story of the void. Thank you for taking this journey with me. If you found value in this exploration, please like the video and subscribe to the channel. Your support makes these deep explorations possible. Tell me in the comments what you think about our place in a universe that is emptying. Does the coming isolation scare you or inspire you? Does the fact that everything is temporary reduce meaning or increase it? The void will win in the end, but we have had this conversation. And that is something the void can never erase because it already happened, because we existed, because for one short moment in the endless history of nothing, there was something, and that something was us. I will see you in the next investigation.